So in this video, we're finally going to see what we're going to utilize the mapping for to be able to, and we're going to implement this with a Jacobian. So before we can do that, we have to talk about the idea of evaluating a double integral using a Jacobian substitution. So let's suppose that we have a region R. It's vertically or horizontally a simple region in the xy plane, meaning that it's not too complex to be able to translate. And then S is going to be another vertically or horizontally simple region in the UV plane. All right, so basically we're going to map T to S. And the transformation T of UV is going to be XY, which is going to be some function in terms of U and V, comma, another function in terms of U and V. And they have partials, they have continuous first partials. Right? Assume that T is 1 to 1, except possibly on the boundary. If all of that is true and the partials are non-zero on S, then we can just take a double integral in terms of xy, and we can translate it into a function or into a double integral in terms of u and v, but multiply that also by the Jacobian. Okay, so essentially what we're going to do is we're going to identify a transformation. We're going to take the Jacobian of that transformation, and then we're going to evaluate a double integral. So let's take the region R, defined by the lines x minus 2y equals 0, x minus 2y is negative 4, x plus y is 4, and then x plus y is 1. Let's evaluate the double integral of 3xy over that given region. Right. Now, you'll probably recall in an earlier example, we actually looked at this. Okay, that was actually this region. Right. So what I'm going to do is I'm just going to cut and paste that region. And we're going to recycle some of the information that we utilized in the previous example. So here's our region, and you'll probably remember that we had a transformation, T, and we eventually found that x was equal to 2/3 u plus 1/3 v. And we also found that y was equal to 1/3 u minus 1/3 v. Right? So that was our transformation. All right. Now, what we can do is we can find a Jacobian from that. All right. So what we're going to do is we're going to take the partial of x with respect first to u. We're going to take the partial of x with respect to v. Then we're going to take the partial of y with respect to u. And then we're going to take the partial of y with respect to v. And we're just going to throw it into a Jacobian. The good news is all the partials are extremely easy. So the first partial is 2/3, the second partial is 1/3, the third partial is 1/3, the final partial is a negative 1/3. Remember, we're going to find the determinant, so we're just going to stick those into our Jacobian determinant. So that's 2/3, 1/3, 1/3, and negative 1/3. Remember, to evaluate, we multiply down, and then we multiply up, and we're going to find the absolute value of this. Okay, so if we look back up here, we find the determinant of the absolute value of that determinant. So we're going to find the absolute value of negative 2/9 minus 1/9, and ultimately that just works out to 1/3. All right. Now this is our Jacobian multiplier, similar to r dz dr d theta, or rho square sine phi d rho d phi d theta. Right? This time we just have a 1/3. Right? We're going to go back up, and if you recall, we also had the bounds for x and we also had the bounds for y in the first example. All right? And now we have our multiplier, so we can't forget that x, or in this case u, excuse me. So remember, u ranged from 0 to 4, or from 1 to 4. Right? And we can see that if we go back up to the picture. Remember, we had that u was x plus y, so u went from 1 to 4. And then v goes from 0 to negative 4. So we had the double integral of some region R 3xy dA. That was the original problem. So here's what's going to happen. We're going to have negative 4 to 0, 1 to 4, where we said that x was 2/3 u plus 1/3 v. So that's 2/3 u plus 1/3 v times y. Remember we said that y was 1/3 u minus 1/3 v. That's from right here. We have our Jacobian of 1/3. So that's the Jacobian. And then finally, since the order was u and v, that's going to be, this should be in here, just ran out of room, du dv. All right. Now notice that this is a single double integral as opposed to having 3 double integrals, which we would need to evaluate the region if it were as a type 1 or a type 2 region. All right, so we're going to evaluate. What we can do is we can factor out a 1/3 from each of the pairs just to make this a little bit easier. All right. So another way to write this would be 1/9 integral negative 4 to 0 integral 1 to 4. And since I factored out a 1/3 and a 1/3, I get 2u plus v, u minus v, du dv. We're going to FOIL it, and then we're going to evaluate. So at this point, it's not too bad. Unfortunately, we can't separate it yet. Okay, so we're going to actually have to FOIL it. So when we FOIL, we have 2u squared. We have a negative 2uv and a positive uv. So that's going to be minus uv. And then finally, we have a negative v squared. Right, that's going to be du dv. We're going to evaluate with respect to u first. So we still have that 1/9. So 1/9 integral from negative 4 to 0. So now we get 2/3 u cubed minus 1/2 u square v minus uv square from 1 to 4. We still have dv in there. So it's going to get a little bit ugly, but not too terribly. So 1/9 integral negative 4 to 0. Right, this is just mechanical at this point. Not sure how that 0 got down there. Alright, so now we're going to go ahead and substitute 4. So this is going to be 2/3 4 to the 3rd minus 1/2 4 square v minus 4 v square. And then we're going to subtract. So there should be a parenthesis here. So then we're going to subtract. Now we're going to sub 1 in. So that's 2/3 times 1 square minus 1/2, or this should be 1 cubed, excuse me. So that's cube, and then 1 square v minus 1v square. And there's still a dv out there. All right, so we're going to simplify all this. All right, let me go ahead and compute that really quickly. So I end up with 1/9 integral negative 4 to 0. So we get 128/3 minus 2/3, which is 126/3, which is 42. We have negative 8v minus a half v, or plus a half v. So that should be 15, negative 15 halves v. And then finally, we have negative 4v squared minus a minus 1. So this should turn into a negative 3v squared. And then we still have dv here. All right. So this shouldn't be too bad. So now we have 1/9. We have 42v minus 15/4 v squared minus v cubed from negative 4 to 0. Okay, so now we have to be careful. Negative 4 is the lower bound this time. So, and notice it's a polynomial, so all the v's go away. So the first term is 0. So we get 0 minus 1/9, 42 times negative 4, minus 15/4 times negative 4, minus a negative 4 squared, excuse me, negative 4 cubed. All right? And at this point, we're just going to finish it off with a calculator, so bear with me. And I ended up with 164/9. Right. So hopefully this illustrates the importance of the use of a Jacobian when we take this not so nice region that we initially had, we translated it into a rectangular region, and so that way we can evaluate it with a single double integral.